All right, so we're just going to continue on, but we're talking about vectors. We've talked about a bunch of different little things: addition, subtraction, scalar multiplication, distance between 2 points. What the next thing that we want to talk about tells us is whether or not two vectors are parallel. And this becomes quite important. You'll see this in a lot of IB questions. They like the concept of parallelism. So basically, two vectors are considered to be parallel if one is a scalar multiple of the other. So if you can find two vectors that are scalar multiples, you've got two vectors that are parallel. So for example, let's just say, and I'll just write this down here, if I had A, and I said A was 2 and 3, and then B is, this is not being my friend this afternoon, and then B, let's say, is 4 and 6. These are scalar multiples of each other because B is 2A. All right, so because of that, we can say that B and A and B are parallel. They're going in the same direction, okay? And so you'll see this often. People will, a question will say something to the effect of, are these are parallel? Or it may tell you something is parallel, and therefore you can find a component that's missing. All right, we'll talk about a lot of practice questions in class, but that's the concept of parallelism. So all you have to do is remember, if they're parallel, they're scalar multiples. All right, then we get into the concept of a unit vector, and this becomes very important. A unit vector, just like the unit circle and those kind of things, anything's a unit is just 1. It's a magnitude of 1. All right, so remember the unit circle had a radius of 1. In this case, the unit vector has a magnitude of 1. So there's lots of different unit vectors, but anything that's a unit vector is a vector that has a magnitude of 1. That's the definition of a unit vector. So what you'll often see in terms of, well, why do we care about unit vectors, is you'll see something to the effect of saying, here's a vector, find the unit vector that's going in the same direction. And then once we found the unit vector, we use that to find out, okay, if something's going 12 kilometers an hour, and I say, I want to know what the vector is, the distance vector is for something that's going 5 kilometers an hour. So we have to basically do a ratio. We convert to the unit vector, and then we go from there. And it's pretty easy to do, but it's just understanding what the concept is. So there are special ones, special unit vectors that we call I and j. I is the vector 1, 0, and j is the vector 0, 1. And so then when we use those, we'll sometimes see them written out in z, which we'll talk about with a third dimension. If you want to write it down now, you can. Z so I is 1, 0, 0, as many zeros as you want. J is 0, 1, 0 if you're in 3 dimensions, and Z is 0, 0, and 1 if we're in a third dimension, just so you know. But what we do with these is we can write out vectors in ij form or ijk form. So if A is 2, 3, like this, that's component form. You could also write it as 2i plus 3j. That's just another way of writing a vector, okay? So if you see that, it means the same thing. The magnitude and all the stuff that we talked about, scalar multiples and on all that stuff, still apply. So in other words, if I gave you B and I said B was I plus J, then when we go A plus B, you're just adding the I's and the J's. So you would get 2 plus 1i, so that's 3i. And then you get 3 plus 1, which is 4j, okay? If you look at, this would be 1, 1 in terms of the components. If you look at them, you get 2 plus 1 is 3, and 3 plus 1 is 4. So if you add them with components, you just get, it's listed like this, 3 and then 4. So very similar, not hard to understand, I don't think, in terms of what you're doing, but just understand that these I's and J's, they are special and they mean something. They mean a unit vector, and they mean a unit vector that has a magnitude of 1 in the x direction, excuse me, or the y direction, or the z direction. So that's the concept of a unit vector. All right? And you're going to see some questions that ask you about that. And I'm going to skip over this scalar product for a second and just go to 3 dimensions to show you this. So 3-dimensional vectors, they have an x and a y and then a z component. And this is the sort of three-dimensional axes. Now you're drawing a three-dimensional thing on a two-dimensional piece of paper or a two-dimensional smartboard or whatever. So it's not easy to plot these vectors. And so you're not going to be asked to draw a three-dimensional vector. It's just too hard to identify where it goes. If you have computers that will let you do 3D modeling, 3D graphing, then it's great and you can see them. But you kind of think of the x-plane as your horizontal, the y-plane as your vertical, the z-plane is the one that's kind of going in and out. All right, so that's it's your depth in some senses. And so you'll see it drawn like this, x, y, and then z. Sometimes you'll see this as the y-axis, the top one, and then that's x and that's z. Or sometimes you'll also see this as x and that's z. It really doesn't matter because you're in 3 dimensions. You can sort of flip them and rotate them as you wish. But they have 3 components, and so it's either x1, y1, z1 in terms of the component, or it's I, j, k. All right. And again, the magnitude, same idea, you just add the third component. So it's a1 squared plus a2 squared. We already talked about that, but then it's plus a3 squared. So if you're in 3 dimensions, that's what it looks like. Okay, and there's all sorts of things you can do with these, but the 3-dimensional vector operations, there they are, just so you have them. But they're basically the same, except you've added a third component. So when you're adding, you add third components together. When you're subtracting third components. And when you're multiplying by a scalar, you're multiplying each of them by that scalar. So that's what 2 dimensions versus 3 dimensions looks like. You're going to have some questions that are going to be 2-dimensional. You're going to have some questions that are 3-dimensional. It doesn't really make much of a difference, but it's important that you understand how to use both. Okay, and if they're parallel, again, they have to be scalar multiples. But if they're in 3 dimensions, you just have to check that all 3 dimensions are scalar multiples. So the example here is 2, 6 minus 4, and 1, 3 minus 2, and 4, 12 minus 8. You have to then say, are they all parallel by looking at the ratio? So this is 4. If you multiply by 4, you get that. Right? If this gets multiplied by 2, you get that. And if this gets multiplied by 2, you get that. So they are all parallel. All right? But that's kind of the concept. That's the idea in 3 dimensions as opposed to 2. Unit vectors, same idea. The magnitude has to be 1. So we go back, we're just quickly going through what we talked about in 2 dimensions in 3 dimensions. So I, j, and there's k. And I already told you about that, but that just gives you the concept of a unit vector in 3 dimensions. Okay, so we have component form, we have I, j, k, or unit vector form. Okay, and so we're going to talk about a couple other things. We're going to talk about collinear points, we're going to talk about scalar products, and we're going to do some examples of geometric things with them, but we'll leave it in this video really just understanding the concept of a unit vector, and then with that unit vector, how to work in 2 and 3 dimensions. And then again, we're going to practice questions, and I'll do some example questions with you in class. It's just trying to get the information to you, right? So I'm going to end the video there. I'll make a third with some of the other stuff in it.